These are just a few examples, much like the problems you're doing for homework, just to get you started on logarithms, basic problems on logarithms. So one of the things that they start you off with in the book is converting from a statement in exponential form to logarithmic form, or vice versa. So for example, if I say the true statement that log, that's not working, log base 4 of 16 equals 2, why is that a true statement? We should always be able to convert that into some statement about exponentials. Well, it says the reason it's true is that the number you need to raise 4 to in order to get 16 is 2. So you just write that down in terms of exponentials. It says 4 to the 2 equals 16. And so that's with numbers. Suppose I say that I'm thinking of some mystery number such that the log base 7 of x is equal to 3. Well then, what can I say about x that talks about exponentials? Okay, it says that if I start with x and I ask what power do you have to raise 7 to get x, that number is 3. Okay, so the mystery exponent, the base is 7, the mystery exponent is 3, and the claim here is that when I raise 7 to the 3 power, I should get x. So in fact, we've actually solved a logarithmic equation, really. We know that x is 7 to the 3rd, which happens to be 343. So that's going to be something we can do. Given an equation involving logarithms, we can solve it by translating it. Sometimes we can solve it by translating it in terms of exponentials. One other notation, something I didn't get a chance to say in class today, or at least for second period, is the log base e. E is a wonderful special base. We've discovered it, at least in one instance, in terms of continuous compounding. Turns out to start to dominate huge amounts of mathematics. Well, log base e of x is so special that a lot of people use the notation ln, for the n standing for natural. So log natural, or natural log, of x. So suppose somebody says that ln of x is equal to 2. What does that say about x? Or another way to say it is, can I solve for x? What is this mystery x? Well, that says that the number I would have to raise e to in order to get x is 2. Okay, so I'll go ahead and do that. I'll raise e to the 2. And what should I get? I should get x, because 2 was the mystery exponent, which isn't a mystery because we actually told you what it was. The exponent that you need to raise e to in order to get x is equal to 2. So x is e squared, which is 7.3 or something like that. It's that number we came up with in our investigations about interest a few times. So that's one example. We can also convert from an exponential equation to a logarithmic equation. If I happen to know, which I do, that 10 to the 5th is 100,000, then that's equivalent to the statement that log base 10 of 100,000 is equal to 5. That's where we started our investigation, with this idea of counting the zeros in a number. The zero counting function applied to 100,000 gives me 5, because there's 5 zeros. And of course the official name for the zero counting function is log base 10. If we happen to know that, let's do e again. E to the, if e to the x is equal to 12, then what must x be? This has a bit of a different feel, even though it's the same kind of procedure. This was a very familiar fact, and it dealt with very simple numbers, and it was explicit, and they're all integers. Here, e itself isn't a particularly familiar thing, although it's an explicit number. It's 2.71828, etc. And x here, I don't really know offhand a number that when you raise e to that number you get 12. It's certainly not going to be an integer, because like e and e squared and e cubed, they're not going to come out being such a nice number as 12. So x is going to be some weird number that we don't actually have a handle on. But at least we can give it a name now. And that might seem like a silly thing to say, but naming things has incredible power. So x is, by definition, it's the number you have to raise e to in order to get 12. Just like here, 5 was the number you have to raise 10 to in order to get 100,000. So it's the ln of 12. So if I want to solve, this is going to be a fundamental thing for us. If I want to solve this equation, and this is going to come up, this kind of equation could easily come up in like a continuous compounding problem. I'd like to get a growth factor of 12. Maybe in the long term, from like early in my career to retirement, I'd like to have my money grow by a factor of 12. That's not implausible. It can happen. And over continuous compounding, what would the exponent have to be in the PERT formula? Well, the exponent would have to be the number ln 12. If I can't calculate this, that isn't terribly helpful to me. But the calculator, in fact, has an ln button. And in fact, let's just calculate that sucker. Oh, it doesn't want to do it numerically. It has to be about 2.4. 2.485-ish. Okay. So there's some examples of problems that you're going to be asked to do. And very similarly, it's really almost the same problem. Some of the problems say use the definition of the logarithmic function to find x. Basically, given an equation with an unknown, a variable, that mentions logarithms, let's try to figure out what the x must be. Let's say log base 3x is equal to 4. What would that mean about x? And so it's really understanding the basic definition of logarithms. X is supposed to be a number that when I look at what power of 3 it's equal to, that power is 4. So it's the fourth power of 3. X is going to be the number 3 to the fourth, which is 9 times 9, which is 81. And so the general rule for that, which is in the book, which is in the book, is that if log, let me use their letters. Don't want to confuse you by putting new letters in. If log to the base a of x is equal to y, that just means the same thing. It's just a different perspective on saying that a to the y is equal to x. In fact, I usually like to write it with the other way. I like to keep the x on the same side and the y on the same side, and it's the log that's moving. This is how inverse functions always work. When I take a function and I move it across, it becomes its inverse function. So the log moves across to the right and becomes the inverse, the a to the function, exponential function. Or if you go the other way, the a to the function becomes the log a function. Okay, so that's a good amount of examples to get you going.